When you look up at the night sky, have you ever wondered about a physics question? What force keeps the stars neatly inside a galaxy? Intuitively, it's gravity, of course. Just like a hammer throw, the rope's tension provides the centripetal force, keeping the ball from flying off. In the solar system, the sun's gravity is that rope, perfectly obeying Kepler's laws. The farther out, the slower it goes. We naturally assumed galaxies would work the same way. The outer stars, the ones farthest from the gravitational center, should naturally be the slowest. But when Vera Rubin, in 1968, first precisely measured the Andromeda galaxy, the universe gave every physicist a loud slap in the face. The galaxy's rotation curve turned out to be flat. The outer stars were moving just as fast as the inner ones. It's like swinging a lead ball on a cotton thread, and not only does the thread not snap, the ball spins faster and faster. This isn't just strange, it openly breaks the very laws of physics we thought we knew. The gravity from all visible matter isn't nearly enough to hold these racing stars. So what provides that enormous, invisible extra gravity? The answer is dark matter. And the star of today's story is a facility built to lift the veil on dark matter, a truly revolutionary one, the Vera Rubin Observatory. To really understand why this observatory matters so much, we first have to go all the way back to the very beginning and get to know the legendary scientist it was named after. This cosmic scale mystery was first cracked open by a woman named Vera Rubin over her entire career. Her story isn't only about a great scientific discovery, it's about living through an era that actively tried to keep her silent and invisible, and about how, armed with nothing but pure curiosity and sheer determination, she made both herself and the universe's deepest truth visible to the world. Vera's love of the stars began in childhood. But in the mid-20th century, astronomy was a thorny path for women. When she applied to Princeton's graduate school, the rejection was blunt. We don't accept women. She later went to Cornell, studying under future Nobel laureates like Feynman. But her master's thesis challenged the mainstream, and 2 journals rejected it in a row. To present her own research, just 3 weeks after her first child was born, she took turns driving with her family 600 kilometers through a snowstorm, baby in tow, to the American Astronomical Society. But after all that hard work, all she really got back was doubt from the audience. Again and again, the world seemed to be telling her in every way it could that women in science were better off staying invisible. And yet, Vera Rubin's entire life turned out to be one long fight against that very invisibility. The turning point came in the 1960s when she joined the Carnegie Institution in Washington and teamed up with instrument maker Kent Ford. Ford had built an extremely sensitive new spectrograph, able to precisely measure starlight's Doppler shift, and from that, the star's speeds. Over the next decade or so, with remarkable persistence, they systematically observed over 75 spiral galaxies. Every time, the result was strikingly consistent. The outer stars were racing at impossible speeds. How do we explain that? Rubin recalled that back in 1933, Astronomer's Wiki had proposed dark matter, but he lacked evidence, so it was never taken seriously. Now, the mountain of data that Rubin and Ford had patiently gathered became the first truly convincing evidence for it. Beyond the matter we can see, galaxies are full of invisible dark matter, 5 to 10 times the mass of ordinary matter. And only then did the scientific world truly start to take dark matter seriously. So even as she was revealing the universe's hidden structure, she was also fighting inside the world of science itself against the very barriers that kept women like her invisible. When she finally became the first woman allowed to observe at Palomar Observatory, she found only men's restrooms. So she cut out a little figure in a skirt and stuck it on the door. That small act symbolized how, for every woman in science, she won the visibility they deserved. Through her persistence, Vera Rubin confirmed that dark matter exists. And decades later, on Earth, at one of the best places for stargazing, Cerro Pachon in Chile, a colossal eye rose up to watch the cosmos with unprecedented power, named after her. At the heart of this observatory is a telescope that breaks all tradition, the Simoniu Survey Telescope. Its design is pure form follows function. To rapidly scan huge swaths of the entire night sky, engineers had to invent a whole new machine. traditional telescope is like our eye, usually two mirrors, a primary and a secondary. But the Simony telescope uses a revolutionary three-mirror design. Light first hits the huge 8.4-meter primary, M1 reflects up to the 3.4-meter secondary, M2, then down to the 5.0-meter tertiary, M3, and finally into the central camera. The most stunning feat of engineering, the primary M1 and the tertiary M3 aren't two separate mirrors, but are ground onto one single giant piece of glass. This wizardry creates an unusually wide field of view, reaching 9.6 square degrees. That means a single photo it takes covers an area of over 40 full moons side by side. It's like giving the cosmos a giant wide-angle lens. If the Simony telescope is the eye, then its retina is the largest, most powerful digital camera ever built for astronomy, the lsst camera. This camera is about the size of a small SUV and weighs over 3 tons. Its sensor is made of 189 separate CCD chips that tiled together for a staggering 3.2 billion pixels. Yes, a full 3.2 gigapixels. What's that mean? To show one of its photos at full resolution, you're looking at over 1500 full HD. That is 1080p television screens tiled together to show it all. This priceless heart took 20 years, built by the US lsst National Accelerator Laboratory. Once it was finished, it had to make an epic move. It flew on a chartered Boeing 747 in a special container full of monitors escorted from California to a remote Chilean peak. From the ultra-wide optics to the ultra-high-resolution sensor, every design detail of the Rubin Observatory serves one single goal: to scan the widest sky as fast as possible, catching the faintest details in the cosmos. So here's a simple way to see it. The whole facility honors the dark matter pioneer, so it's called the Vera Rubin Observatory. The telescope itself, thanks to key private donors Charles and Lisa Simony, is named the Simony Survey Telescope. And that powerful camera, with its upcoming 10-year survey, keeps the project's original name, the Legacy Survey of Space and Time, or lsst. With such a powerful eye and retina, the goal obviously isn't to slowly stare at just one single target. The Rubin Observatory's real power lies in the way it actually operates, an unprecedented, ultra-fast survey that sweeps across the entire sky like nothing before it. After the camera arrived in March 2025 and the first images came out in June, over the next 10 years, it will film the entire southern sky as an ultra-high-definition time-lapse movie. Its pace is astonishing, about 1,000 images every night, scanning the whole southern sky roughly every 3 days. This kind of survey will unleash an unprecedented tsunami of data. The Rubin Observatory will generate, each night, 20 terabytes of data. In its first year alone, it will collect more than all the data ever gathered by every optical telescope in history. But data alone still isn't enough. The real revolution here lies in speed. Within just 60 seconds of a photo being taken, the observatory supercomputers finish processing all that data, automatically comparing it to the previous night's images and flagging anything that has changed. And the moment something big happens, say a distant supernova suddenly explodes, or an asteroid comes flying past, the system immediately fires off an alert to astronomers all around the world. It's expected to send up to 10 million alerts a night. So it's like a cosmic 24-hour news channel, reporting the sky's every move in real time. For most of history, astronomy was basically a series of still, static snapshots. But from this point on, the Rubin Observatory will turn the entire night sky into a living, constantly updating movie. This is the golden age of time-domain astronomy. Okay, so we know the Rubin Observatory has an ultra-wide view, an ultra-high-res camera, and ultra-fast reactions. So with all of these incredible powers, what frontier questions is it actually going to answer for us? And that brings us to its core mission over the next 10 years, the lsst, an epic exploration of the cosmos told in 4 grand acts. Act 1, and the most important, carries on Vera Rubin's legacy, mapping the dark. So you might naturally ask, how do you actually see invisible dark matter? The key is weak gravitational lensing. It's like looking through pool water at the tile grid on the bottom. Ripples make the grid look warped. In the same way as light from these distant galaxies reaches us, the foreground dark matter acts just like that restless water, subtly warping each galaxy's shape into a faint little ellipse. For any single galaxy, that tiny distortion is actually smaller than the background noise. But the real strength of the Rubin Observatory is that it can use its ultra-high resolution to analyze the shapes of billions of galaxies, all statistically at once. But when millions of galaxies are all stretched slightly in the same systematic direction, scientists can work backwards to map that invisible foreground water, that is, where the dark matter sits and how much of it there is. Act 2 is about our very survival, the cosmic sentinel. How among billions of stars do you find the asteroid that might hit Earth? The key is how often Rubin revisits the sky. A traditional survey might happen to catch a moving dot of light tonight, but by the next time anyone looks, it's already long gone. Every few nights, Rubin returns to the same patch of sky. So it can connect scattered dots from different nights, like a connect the dots puzzle, and quickly compute an asteroid's full orbit. Its custom HelioLink 3D algorithm can lock onto a target with as few as just 2 observations. This takes planetary defense from a needle in a haystack to nearly total surveillance. Act 3 takes us on a journey back into the deep past, galactic archaeology. Our Milky Way is a galactic cannibal, growing by devouring its neighbors. So how do we find the victim's remains? These dwarf galaxies, torn apart by gravity, form faint streams spanning hundreds of thousands of light years. They're like a few grains of salt on a black beach, extremely hard to spot. Past telescopes either saw deep but too narrow, missing the whole stream, or saw wide but not sensitive enough to see them at all. The Rubin Observatory is the first telescope that's both ultra-wide and ultra-deep at once, and that rare combination lets it bring these faint, ghostly skeletons in the Milky Way's halo into view, piecing together how our galaxy evolved. Act 4 focuses on the universe's most violent moments, the transient universe. How do you catch a supernova the instant it explodes? The answer is difference imaging. The computers take the image captured tonight and carefully subtract the reference image taken just a few days earlier. Anything at all that has changed in brightness or in position suddenly pops right out of the subtracted image, standing out clearly like a single bright spot. That's the secret behind 10 million alerts a night. This is vital for multi-messenger astronomy. So the moment LIGO picks up the gravitational wave signal from 2 neutron stars merging, it can only point us to a rough patch of sky, and that's when the Rubin Observatory steps in and combs through that whole region, inch by inch, hunting for the sudden flash of kilonova light that matches that event. But this grand cosmic movie faces a challenge from Earth. The fast-growing swarm of low-orbit satellites, especially networks like Starlink. The bright trails they leave across the sky are for an ultra-wide, highly sensitive survey like Rubin, like someone waving a flashlight in front of your camera, badly polluting precious data. Right now, astronomers are actively negotiating with the satellite companies, fighting hard to protect the night sky for everyone. And it makes us stop and reflect. Even as we reach out to explore the cosmos, how do we protect this night sky that belongs to every one of us? And all 4 of these grand acts will be driven by one unprecedented flood of data. And this data tsunami is now reshaping the face of astronomy. The traditional observe then analyze model is being replaced by a whole new paradigm. Astronomy is shifting from an observation-driven science to a data-driven one. Future astronomers can't just know physics, they must also become data scientists. Because no single human can manually check 10 million alerts a night. we have to rely on artificial intelligence and machine learning algorithms to automatically sift and sort out the interesting targets. And yet, perhaps the most exciting part of this revolution isn't the machine's intelligence at all, but the brand new possibilities it opens up for ordinary people. One of the Rubin Observatory's most central missions is to open up all of its data to the entire world. And this is far more than just a movement to democratize science, it's also a personal invitation directly to you. Through citizen science platforms like Zoniverse, the observatory invites everyone to join this great exploration. Wherever you are with just internet access, you can become a citizen scientist. You can help scientists across countless images find rare comets or spot active asteroids spewing material. And this really isn't just simple outreach, it is genuine scientific research. Against the flood of data, human pattern recognition is still irreplaceable. And every single click of yours out there could turn into a brand new discovery. From a young woman quietly peering at the night sky through a homemade cardboard telescope, all the way to a colossal eye high on the peaks of the Andes, gazing into the depths of the cosmos, the Vera Rubin Observatory story is at heart one of legacy, of innovation, and of a curiosity that is never satisfied. In a 1995 paper published in the astrophysical journal, Vera Rubin summed up her discovery with a deeply humble line. She said, "In a spiral galaxy, the ratio of dark to visible matter is about 10:1. Maybe that's also our ratio of ignorance to knowledge. We've just graduated from kindergarten, and we're maybe in 3rd grade. And that one humble sentence captures the entire spirit of this observatory perfectly. It isn't a monument built to declare some final victory. It's much more like a humble engine, built from the ground up to go out and explore the vast unknown. Its mission is to confront the 95% of the universe we still know nothing about, dark matter and dark energy. And perhaps the greatest discovery in this entire quest won't be any of the ones we've already written into the plan, but the ones we can't predict at all. The true unknown unknowns, still waiting out there in the dark. Vera Rubin spent her life in a male-dominated scientific world, winning women a place at the table, and, in our bright view of the cosmos, winning the vast dark its rightful place. Now the observatory that bears her name will continue that double quest, seeking light in the dark and truth in the unknown. If this upcoming journey into the cosmos excites you too, please like and share this video with a friend who loves the stars. And don't forget to comment down below and let us know, out of these 4 great acts of discovery, which field are you most excited to see the Rubin Observatory break new ground in? This has been the very first episode of our Slow Science series, and going forward, we really hope to keep this gentle, unhurried pace, telling science stories that are truly worth slowing down for. If you have any suggestions at all, do let us know down in the comments. Thanks for watching, and we'll see you next time.